to record the things during this online meeting. Yes, the chapter title is Sheet Metal Work and the subtitle is Developments. The development is a view. It is a valuable view if the work of course to deal with it is a sheet metal work. Okay, I'm going to clarify the meaning or the definitions. Before scrolling the slides of this presentation, well, I think it's going to be just to the point, say, to answer the question, what is sheet metal work? Saying sheet metal work, we mean what? Sheet metal work, actually, or sheet metal is a phrase. It is quite common, well, in the jargon, okay, of technicians, engineers. Okay, saying sheet metal work, we mean what? Well, the component having a thickness greater than 0 and less than 12 millimeters. And well, it is just the component, okay, it can be manufactured, it has been manufactured, just bending, folding, well, right prismatic sheet. See this figure? Well, okay, then take a pointer and then identify them saying figure which one I mean, which one, say figure A. And this is figure B. In figure A, it looks like photograph, well, pictorial drawing, okay? It is just by definition a sheet metal work, sheet metal component. And so the studying on, working on such an object is called sheet metal work. Well, what is that? See, first of all, the thickness. Well, thickness is the same here, 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 okay? Well, initially, it was such a flat sheet, well, with such special boundaries, okay? Well, find at the beginning, of course, from the stock, well, most of the cases, depending on the main geometry of the object, of course, well, most of the cases have the sheet in rectangular prismatic shape. And then, well, take a rectangular prismatic sheet and, well, you know, the boundaries to have in size, in shape, okay? Through this figure using special pens or directly while using some welding robots, okay? Through this one, this figure, this projection, it shows a sheet metal work as unfolded, okay, flattened, flat over a plane. It's called development, okay? Well, in this photograph, this figure, figure A, it is the sheet metal work. It's a sheet metal component. Well, for this component, this view is called development. It shows the sheet metal work as unfolded, okay? Unfolded. Well, this is a valuable projection. It shows a sheet metal work as unfolded, and that projection is drafted using special pens, scribing pens, and then when along the boundaries, then the sheet is cut. Well, after cutting stage, then, well, we know along which paths, these are the paths, the sheet metal is to, when folded, is to be folded. Fold this part along this path, fold this part along this path, and so on. Then at the end of the folding stage, you have the object. Initially, it was a two-dimensional right prismatic figure, two-dimensional figure development. And well, it was initially a right prism, but after folding the sheet metal along the specified paths, then it is going to be a 3D object. Strange in shape. Okay. Well, this is important. This is the threshold value. Well, in speaking or identifying the work as sheet metal work, we use this threshold. If the thickness of the right prism, thickness of the stock, so well, thickness of after the folding each of the features, combined features, is less than 12 millimeter, then we say sheet metal. Okay? Sheet metal. In Turkish speaking, we say saç levha, saç levha. Okay, sheet metal. And of course, using a sheet metal, while folding the sheet metal along specified paths, we can obtain the object in the desired form. It is called sheet metal work, sheet metal component, and the process is called sheet metal work. Okay. Well, from this example, can see the value of this projection. If you have the development, it is called development. Flattened view of the sheet metal component is called the development. Development. Development is quite valuable. If it is given in the correct shape, correct size, then can ensure that when we fold the sheet metal along the specified paths, then finally, starting from this stage, can reach to that final form. Okay. After delivering such sentences, well, open a parenthesis and then see some examples. For instance, well, here, this is no doubt an assembly, the model of an assembly, the main part of desktop computer. Okay, the cover of the desktop computer has been disassembled here to allow to see the inside of this box. If you see the object in this direction, yes, it is like a black box, but thanks to removing this cover, yes, left click indicate and deselect the visibility, and then, well, the rest can see the inside. If it is the model of an assembly, then we're saying, remove the visibility of the components from the screen. We can see what is the thing at the inside. But inside of this black box, we have, as it is very well known, well, here, this is the coolant, tweeters, fan, and extended surfaces. This cooling system is to keep the temperature of the central processing unit, okay, well, less than the maximum allowable value. Okay, well, we have the RAM cards and screen card, the etc., capacitors, some resistors, and of course, no doubt, well, between them to carry the data, digital or analog data, we have cable connections. Okay. Well, there is a very sophisticated electronical part inside of this box. How about the outside? Well, the case. Well, the cover of this computer, this cover, okay, well, this box, it is to keep the electronical components, okay, from the outside, is as a whole sheet metal work. For instance, well, indicate this component of the computer with a click in this virtual environment, of course, and then right-click the mouse and select Open option. This is the thing, it can be done to isolate the selected part of an assembly, okay, from the rest. If you select Open option, then you can find the selected one yes, as separated from the rest, where in part environment, you can find it in part environment. Well, this is, you see, a sheet metal work. It's a sheet metal component. Its thickness is the same. Well, here, all the parts, okay? And well, it has been folded. Initially, it was a flat sheet, but after folding, well, the folding lines were taken annotator, well, this color. Along this edge, it has been folded. Along this edge, folded, and here another edge to fold, one more edge, and so on. After folding stage, then we have the component in this final shape and final size. Okay. Well, how about the unfolded form of this sheet metal work? Well, today in Inventor, well, it is a quite easy thing to see it is as unfolded, the sheet metal work as unfolded, because there is an algorithm at the background and the corresponding code program, high level, written in high level language. And as the users, we have just a corresponding push button. It is written over here, go to flat pattern. Okay, if you clicked on this one, you can see the unfolded form of that sheet metal component. Okay, this is the sheet to have at the beginning, in shape, in size. And while the highlighted lines, Inventor uses just as if it were axis of symmetry, but this is not axis of symmetry actually. It uses long dash, short dash, but here, if it is sheet metal work, this appearance, this simulation to say that that is the path. Along this path, the sheet metal is to be folded. Well, this is the path along which fold the sheet. Well, how many degrees in which direction? Inventor can answer this question if you clicked on this button, bend order annotation. Well, after clicking on this button, can see the answer of the question. Inventor, as if it were an experienced engineer and technician on sheet metal works, as if your assistant, associate engineer, Inventor saying that, well, first start from here. Of course, after having the development, well, it was initially what? Well, initially, this sheet in this example was in this initial form and size, rectangular prism, rectangular prismatic sheet. Okay. Well, from the stock, from the market, find such a rectangular prismatic sheet, and then, well, be able to try to erase. And then, well, try to, of course, using some robots today, it is possible, draw this contour. You know, it is to be in which shape. And then after drawing the boundaries, scribing the boundaries of the sheet metal component, using a certain cutting technique or tool, be able to cut the sheet metal. Have the sheet metal in this form. And then, well, Inventor says that along this path, fold this part of the sheet metal. Okay, along this path, second order, well, fold it. And then Inventor says that after folding this part, then see along this edge, where sequence is important, fold the sheet. After folding this part, folding the sheet along this path, then, well, come to here and fold it along this edge. and then along this path, etc. Yes. If, of course, it is the sheet metal environment, and well, the sheet metal component has been modeled, then yes, using these tools, okay, sheet metal defaults, go to folded part. If you clicked on this, then you see the model as folded again. If you clicked on go to flat pattern button, then you can see the unfolded form of the sheet metal component. If you clicked on this, then inventor inform you in which order, in which sequence the sheet metal, okay, such a sheet metal is to be folded for having in the end this final form. Okay. Beforehand, to be able to achieve such things, well, saying beforehand, I mean 30 years ago or maybe more, there was no computer, okay, no inventor, no AutoCAD. Well, to be able to achieve such things, well, the thing to achieve is that, say, development. Okay, for having this sheet metal component, which projection is needed to scribe over the surface of a sheet metal? To answer this question, we offered two complementary courses in our curriculum, Descriptive Geometry 1, Descriptive Geometry 2. 1 year course, 2 semester courses, Descriptive Geometry 1, Descriptive Geometry 2. And then, well, thanks to gathering the learning outcome from such courses, then a student might be expected to achieve the things on a sheet metal work. But today, well, what I say, 2 hours, maximum 4 hours is a reasonable period to complete the chapter for being educated. Okay. Well, another example, yes, here, this is a sheet metal work. Well, we have some banded features and some, say, empty spaces. Punching process has been applied using punch tool, cutting, and there's an emboss here. Sheet metal work has been, this sheet metal has been plastically deformed. Well, you see here, the process, it has been applied. Okay, well, annotation tool, let me invoke the tool of IPEVO. You know, this software is more powerful to have an annotation in making such a presentation. Okay, take a pencil. Well, this part you see is an empty space. The cutting process has been applied. But this part you see, we have a cavity, blind cavity in rectangular prismatic form, but it is not a cutting. Well, it has been embossed. It has been, this part has been plastically deformed. Okay, thanks to applying the plastic deformation process, well, you see, it has been realized we have such an embossed part. And this part of the work is a folded portion, okay? Along this edge, it has been folded. If you make zoom in to such a part, you see we have an edge along with the sheet metal has been, this part has been bended. To be able to prevent any tearing, to be able to prevent having very great stress concentrations, well, such a special cutting is needed. It is called relief. Okay, relief is to be in a standard size, recommended size and shape. C, relief. If you have a new generation software, well, sure, creating the model of a sheet metal component, such complementary entities are automatically created. Relief is created by the software. Well, here and there we have the reliefs. Without having such reliefs, if you attempt to bend the sheet metal in, of course, not virtual environment, but real environment, real life, then sure, at the beginning, at the end of such a bended part, there will be extremely large stress values, and the atomic bonding forces most probably will not be sufficient to balance the applied forces. So, well, there will be a failure here and also there. But reliefs, using the reliefs, creating such special cuttings, we prevent to have undesirable excessive stress concentrations. Well, if you wonder the flattened form of the sheet metal work, you know how, clicked on this one and then see flattened form. Okay, in which order this sheet metal is to be folded? Clicked on this button. Inventor says that first fold this and then along this path apply the folding process one more time. Another example, a very strange sheet metal component. Okay. Now, how you can know at the beginning it was in which shape? Quite difficult question, but today, well, if you use this facility, it is an easy case. Click on this button and then see. It is appearance at the beginning to have development. Of course, the technical drawings are important for this sheet metal work. Well, not only the orthographic views, principal views, for instance, say this is the sheet metal work and then sheet metal component, sorry, and then say that is the selected front side of the body, and that is the sense for the rays of sight to deliver, to send from the eyes of the observer. Okay, so that is the direction to observe the object to output top view. That is the direction to observe the body to have the left side view. Okay. Well, if it is a sheet metal component, rather than the principal views, development is more valuable. The most valuable projection is not the front, not the left, not the top, not the principal views, but the development. Because development is needed for sheet metal component. It is the projection, okay? Well, it corresponds to the unfolded appearance of the sheet metal component. And that figure is to be spread over a prismatic, right prismatic sheet metal. And then along the boundaries of the development, the sheet metal can be cut and thereafter can be folded. Okay. Now, inventors quite capable, powerful in creating the developments. For this sheet metal component, well, let us see how the development is created. Start the view creation process, and then after having the paper simulation, yes, for informing the reader, well, which side is front side, and if the object is observed to output the image in which direction, well, the appearance of the object, the projections of the object, say, create the front view, top view if necessary, top left side view, the necessary principal views. That is okay. But looking at front, top, left, then technician cannot understand, yeah, well, at the beginning, which figure is to be used to scribe the boundaries over a piece of sheet metal. Well, start the view creation process. Only for sheet metal works, base view creation button is to be used or is used one more time. You know, clicked on this button only one time, it is said, if the views to create will be what? Principal and auxiliary views. But if you're going to create, well, a development, this means the object is a sheet metal work, sheet metal component, then, well, it is to be clicked. Clicked on base view creation button one more time. Okay, but in the view creation dialog box, don't forget to select this radio button. You can find this radio button, okay, flat pattern option, if the work is a sheet metal component, of course. Well, you can find this facility if at the beginning you selected the correct template option. Okay. I'm going to clarify this sentence in a few seconds. Select flat pattern option. It is the option to create not a principal view, but to create a development. And select a suitable scale factor. And then, yes, find an empty space on the paper for this development. This is not a principal view. This is a special view. It shows the sheet metal component as unfolded. Yes. That is on the page. Which view is the most valuable one? No doubt, it is the development, this view. After creating the view, then, well, you find such lines. It looks like axis of symmetry, but certainly if it is just over a development, well, unless otherwise mentioned or well distinguished, sure that this line on the development, it is to find is the mid path of the mid part of the path line. It is the path line. Well, along this path line, the sheet is to be folded. These are the folding lines. Okay, not axis of symmetry, folding lines. To be able to have the sheet metal component in this shape at the end of the folding process, like this, then yes, here, well, along this edge, along this edge, along this path, sorry, path, and this path, the sheet metal is to be folded. Well, this is going to be the question of the technician. Okay, sir, well, I see that this is just a folding line, but what about the folding angle? Whether this part gonna be folded 90 degrees, 40 degrees, 30 degrees, well, it is a reasonable question, and it is a challenge actually to have to say something looking at this view. But if you select annotation tab and then, well, clicked on bend button, it is to bring the bending nodes, folding nodes, the nodes to use to consider at the folding stage. And then, well, if you know that this is the line, it corresponds to the path along which the sheet metal is to be bended, indicated with a click. Then see the value. Inventor says that, okay, then fold this part along this path in the down direction, and folding angle is 90 degrees. And along this edge, have a quarter cylinder. If it is the folding angle, 90 degrees is the angle, then, well, the over here, there will be a quarter cylindrical transition part. Well, for that transition part, the rounding radius is 0.2 millimeters. How about this one indicated? Well, it is to be bended not in down direction, but up direction. Well, along this path, down direction 90 degrees, down direction 90 degrees, in the down direction 90 degrees. Sorry, not 90 degrees, 10 degrees. Well, this is not 90 degrees, 9 degrees. Okay? Who can know that how many degrees it is to be bended or folded? Inventor knows and directly answer the question, 9 degrees. If the precision is to be higher, then say that 9.1 degrees. Okay. Quite valuable things. Huh? This is what, see the solid model. There is a punch over here, plastic deformation. Okay. Well, applying punching process using this tool, it can be created. Okay, then for this part, what is the punching direction? Click on punch button and then indicate this one. Well, with a leader line along the shoulder, it is written in the up direction. Well, the angle, cone angle, there is a conical surface. If it is embossed, well, we have a conical surface between two flat surfaces. The cone angle 270 degrees. Why the leader line just uses or has only the inclined part? Press escape button, answer the question, because, well, the dimensioning tool of the software has not been configured yet. Styles editor, clicked on this button. And then we'll select dimension option, last option after clicking on this cross and dropping this list. And then, you know, precision, well, select the precision depending on the values of the deviations for the functional and non-functional dimensions. Well, say something, whether if the, well, the deviation starts from tenths, then this means you need to show the nominal value as an integer. You know, you learn such things. So, well, configure the dimensioning facility. At the beginning of the extension lines, there should be 2-3 millimeters empty space, etc., etc. You learn all of such things. Nodes and leaders, okay, then we'll select this option to have the leader lines with the necessary horizontal tails. And then, well, if you clicked on thereafter punch button and indicate the boundary of a punch, then you can see the annotation. You can have the annotation as written along the horizontal shoulder. Indicate this, and then, well, these are complementary, very valuable nodes. Well, in addition, those, of course, show the dimensions. How about the size of this part of the development? Yes, it is needed. Well, show this part and say that from this edge to the folding line, the distance is 69. Okay, so on and so forth. Well, for the reliefs, well, since the relief is a standard relief, not necessary to show the dimensions. Okay, well, at the reliefing process, we use a standard special reliefing tool. So using that tool, we cut the material and have this empty space in the correct shape and size. So, well, since it's a standard relief, well, not necessary to show the dimension, because an experienced sheet metal worker can know which tool is to be used if the sheet metal thickness is equal to such a value. If it is 1 millimeter, well, the relief size is to be like that. If it is greater than 1, it should be in that order, etc. These are all well-known things for an experienced engineer or technician. Okay, well, after this direct to the point, direct, introduction, then, well, turn back to the presentation, the slides of my presentation, and then, well, by the break time, allow you to see the things on the pages via scrolling. I don't want to say blah, 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 blah. Just allow you to see the slides of my presentation. Yeah, well, standard sheet metals in the market. What are the standard thickness values? Go to market and then ask the shopkeeper, I want to purchase a sheet metal. Okay, its thickness is 0.7. Sorry, you cannot find it because 0.7, yes, is not a standard thickness. In the market, you can find sheet metal. Its thickness is 0.8. Flat sheet, foil sheet, flat sheet. Well, the minimum thickness 0.5, maximum thickness 3. Okay. If the material is stainless steel, aluminum, yes, well, can find the standard thickness values in the market. And well, and in Turkish, this is from Turkish standards, width, and this is the height of the rectangular prismatic sheet. Okay. Well, in the market, be aware, you can find a sheet metal, sac levha, in Turkish we say, in which size? Width, height, or vice versa. And if the width is 1 meter, height is 2 meters, then well, the standard thickness values 0.4, yes, it is available in the market. But thickness 0.4, if you say that, well, the width is 1,500, then shopkeeper will say that, sorry, sir, there is no such a sheet, you see, in the market. Cannot find sheet metal in this thickness, or in that thickness. Okay. If it's a coil sheet, rulo in Turkish, then well, see, these are the width values. Since it's a roll, in the other direction, well, depending on the size of the roll, it may be practically very long. Okay, and the standard thickness values. Okay, continue to scroll. Well, here there is an illustration. It shows the folding, bending stage. Okay, we use special points and special, well, dies. Okay, and well, knowing the theory and also the, well, the engineering experience about sheet metal work, we fix what should be the, say, minimum folding angle. We use at the bending stage, folding stage, specially designed machines, bending machines. This is a manually operated bending machine. Okay, for cutting the sheets, we use special, well, shear cutting scissors. Okay. And well, for bending bars or structural elements, we use special bending dies, clamps, and some other complementary tools. Well, this slide, it is illustrated for having a cylindrical, well, pipe made of sheet, metallic sheet, well, which development is needed. For having a hexagonal prismatic channel, okay, in such a shape, this is the top view, this is the front view, which figure is to be drafted over a flat sheet metal? What is the development? Here is the answer. Well, for having such an adapter, you see here, imagine, well, this part of the ventilation channel in the given example is rectangular prismatic channel. It is order of magnitude is over here in this size. but well, after this transition part, the rest of the channel is to be smaller in size because we need to increase the speed of velocity. Well, while you're taking the fluid mechanics course, your teacher will inform you, well, the volumetric flow rate. To say volume, I use this symbol. Looks like capital V with such bending arc, such curly arc. And then, well, put a dot. It is to say volumetric flow rate. How it can be calculated? Multiplying the cross-sectional area with the average speed of the flow. Within the channel, through the channel, we have, for instance, conditioned air flow. Air is flowing. Okay, it has a certain average velocity, flow velocity. If you multiply flow velocity with the cross-sectional area, we obtain the volumetric flow rate. Okay, the unit of this in SI unit system is cubic meter per second. From Bernoulli equation, what is Bernoulli equation? While you're taking fluid mechanics course, you're going to deeply be informed on the answer of this question. It says that, well, if the flow is steady state, not transient flow, then, well, at any cross-section, this cross-section or that cross-section, the volumetric flow rate is the same, the constant. So the volumetric flow rate written at this cross-section is equal to volumetric flow rate written at the other cross-section. So this cross-section denoted, say, cross-section 1. This cross-section, say that cross-section 2. So, since the volumetric flow rate is the same, then we can write this equality. Flow velocity at the first cross-section times the cross-sectional area, A sub 1, is equal to flow velocity at the second cross-section times the cross-sectional area. From this equality, in other words, can say that governing equation, it is obvious. Well, decreasing the cross-sectional area, we can increase the flow velocity. The flow velocity at the second cross-section is equal to volumetric flow rate divided by the cross-sectional area. Well, if this term is to be increased, obvious that we need to decrease the denominator. Well, say that in this example, it is the case. We need to increase the velocity of the flow. Well, the question is that, okay, then to be able to connect a larger channel and a smaller channel, obvious that we need to have an adapter, transition part. Okay, such a part. It is needed. It is by definition a loft, but here, since the work is sheet metal, these are sheet metal components. This loft is a sheet metal component. Okay, well, which figure is to be drafted over a flat sheet such that after folding to have the adapter in the correct size, correct shape? The answer for this loft is over here. Development. Well, here there is a theory part, very briefly, of course. K factor is the common technique in theory. During the bending folding stage, well, can find at a certain cross-section of the sheet metal neutral plane. It is not compressed, it is not, say, stretched, but well, other layers, other part of the sheet metal, depending on the direction of the folding, will be in tension the opposite side will be in compression. What is K factor? How it is used? Bending allowance is needed here. It is important. Well, if we do not have such an allowance, such a, say, transition part, well, sure, while we're bending the sheet metal, we're gonna have very great stress concentrations. Okay, such a bending allowance is needed. It should be in a special size. It is minimum size is specified. And well, at the marking stage, at the development drafting stage over a flat sheet metal, well, we should mark the bending allowance, the boundaries of the bending allowance. There must be such an additional part. This part is to be used for having such a transition part from this feature to pass to the other feature. Bending allowance, it is said bending allowance. How it can be calculated? What should be the size of the bending allowance to draw, to bound over the surface of the flat sheet? That question is not an easy question to answer, but if you have the software, if you're using the software, well, ask it to the inventor, to the software. Software can easily answer the question. Okay, well, this slide you can see the bending allowances order, and then, well, in K-factor method, well, bending allowance can be calculated using this expression. And well, if it is used, this equation is used, can prepare such a table. Well, all the numbers, well, those can be found referring to such a table are available in the database of Inventor. Inventor, using it is code, subprogram, subroutine at the background, can calculate the bending allowance, and creating the model of sheet metal component, it is used by the software, and Inventor can create the reliefs, can create the bending allowances, for our convenience on behalf of us at the background, inherently automatically. Okay, relief. Well, as it is written over here, if there is no relief, then, well, it causes tearing. When this part is attempted to be folded, to fold, then here there will be very great stress concentration and tearing. Well, such a tiny tear will appear, and then it will propagate, and it is probably going to be broken. But if we create such a relief, it is in the recommended size with depth values. Well, 2 times the sheet thickness is the recommended order. Bending radius plus thickness is the recommended order for the depth of this channel, blind channel. Inventor knows all of such things, and while we are applying the folding process in the virtual environment, relief is automatically created. And then after saying such things, then address. Well, how you can have the necessary tools, okay, in Inventor environment. The answer is that after fixing the unit of measurement, not by selecting this very well-known template option, not this one, but selecting the other. It is written sheet metal. If the component is a sheet metal work, sheet metal component, then to be able to make the life for yourself easy, to be able to easily create the development at the viewing stage, to be able to allow the technicians to see the unfolded form of the sheet metal component, yes, select this template option. Okay. Well, this is the last slide of my presentation. But here, of course, bringing the slides to the screen, well, I delivered few sentences very briefly, not in detail. Why? Although, you know, it is quite a well-known thing that in Middle East Technical University, especially in my courses, I use spoon feeding method. Why? Delivered few sentences. Before the break time, answered the question because, well, in my lecture notes, I talk about all of the necessary things in detail, again, using spoon feeding method. Okay, well, open MECH class, and then show the hyperlinks for your clicking. MECH class, okay, login before the break. Course code, I selected the course from the navigation list. Okay, and then, well, this week. Scroll the list of the weeks, and then, well, the week extends from the 3rd to 9th of May. Sheet metal work part 1. Sheet metal work part 2. Well, these links are to hear me while I'm talking about the sheet metal works in detail. Okay, clicked on this hyperlink and then see what the Murat Hoca is saying in YouTube involved. This is the cover page of my presentation. Sheet metal work. Yes, sheet metal work is a key phrase in the jargon. Okay, if you say that, what is that? Yeah, it is a sheet. Meaning what? Be the one to use. And it is no doubt the surface, this and others, tilted and then try to allow you to see the green lines. These are to be so on and so forth. Yes, yeah, well, these are the hyperlinks to access to such video records. And over there you can find Murat Hoca, while Murat Hoca is explaining the things in detail as complete. Okay? This two hyperlinks to complete, to watch for completing the theory part, lecture part 1, part 2. But the others, as it is written over here, CAD application. Okay, then knowing such things, you know which one is called sheet metal work and what is development, what are the standard thickness values, what is relief, etc. Then we'll see how about the rest. In Inventor, which template is to be selected, and after opening the software and selecting from here sheet metal option, sheet metal, do not select Deutsche template, Germany template, select ISO template. And then yes, along the home ribbon, you see it is not written home, but sheet metal ribbon, sheet metal tab, sheet metal ribbon. Instead of finding, well, extrude, revolve, etc., along sheet metal ribbon, you find face, flange, contour flange, lofted flange, contour roll, bend, fold, drive, cut, corner seam, punch tool, etc. Okay, and sheet metal default. Well, after opening the software and bringing the being in the environment sheet metal sheet metal component creation environment, well, the following thing in order to deal is that configuration sheet metal default. Clicked on this one and then, well, clicking on this pencil button before doing this, see that automatically selected unfold rule is K factor rule. Okay, clicked on this pencil point and then, well, bring this configuration dialog to the screen, and here fix the sheet thickness. Okay, thanks to this configuration stage, then inventor can know that the thickness of the sheet metal is that, and according to create the reliefs, for instance, in correct size. for instance, clicked on this button and then see the configuration for the relief in K-factor method, where the minimum remnant, relief depth, relief width. These are all in recommended values. Inventor knows all of such parameters and the coefficients, then correspondingly can create the reliefs in the correct shape and correct size. Configuration stage. Okay, and then you can start to deal with the rest. How about the rest? Well, here, watching video record 48, 49, and 50. You can find all the answers of all the expected questions. So, my dear students, since these video records are in detail and complete, okay, then, well, I want to say that after the break, use asynchronous technique and start from this video record, 46. Use the time, not under my supervision or observation, okay? Well, you may leave the Cisco classroom after the break, or just right now, have a break and then on the rest. No need to turn back to Cisco classroom. You can study on the rest using asynchronous technique, asynchronous manner, while watching this video records. Okay, well, knowing and ensuring that these video records are in detail and complete, well, this is just my assignment. By the next meeting time, it is tomorrow, okay, well, complete this part, complete studying on this chapter. Today, say that, finish this chapter. Next meeting, it is tomorrow. I'm going to make an introduction to assemblies, assembly modeling. Okay. Study on this video records and then be ready to take a short exam. Why not? Tomorrow, sorry, tomorrow I may ask you on some questions to check whether you watch this video records and you studied on the chapter. Okay. There may be a pop quiz tomorrow about sheet metal work. Okay, dear students, stop recording.